had to be launched from the underside of a modified B-52 at 45,000 feet because the XLR-99 rocket engine would burn through all of its fuel in just 2 minutes. Not only did the X-15 set speed records, it also went past the point of where space officially starts at 100 kilometers, 62.1 miles on 2 occasions, both times piloted by Joseph A. Walker at 105.9 kilometers, 347,000 feet and 107.8 kilometers, 353,000 feet. Although in the 1960s the US Air Force considered space to start at 80 kilometers or 50 miles, any crew that flew over the 50-mile limit were awarded an astronaut badge. 13 of the X-15 flights went higher than this, and 2 of the pilots, Neil Armstrong and Joe Engle, went on to become fully fledged astronauts in the Apollo and Space Shuttle programs. But apart from being a record-breaking aircraft, research from the X-15 program led to things like the first full pressure suit that would work in space, the first use of reaction controls, the little gas jets that position spacecraft in space, the first use of superalloys in the plane structure that could withstand the heat of a hypersonic re-entry, and the development of the first large restartable, throttleable rocket engine, the XLR-99. These are a small selection of the developments and discoveries that would go on to contribute to later space programs, including the Mercury, Gemini, Apollo, and the Space Shuttle. In the early 1950s, research that started with the Bell X-1, the first supersonic plane, began looking into the problems that would be encountered by spaceflight. At the time, it was still unknown as to what would happen to the stability as well as other issues of the craft when travelling at hypersonic speeds. That's between Mach 5 and Mach 10, or between about 3,800 and 7,700 miles an hour, 6,200 to 12,400 kilometers an hour. This will be the type of speed that will be required to get to the edge of space and the re-entry. In 1952, the National Advisory Committee for Aeronautics, or NACA, NASA's predecessor, started looking into the problems, and by 1954 they had contacted both the US Navy and the Air Force to propose building a research aircraft that would become the X-15. By 1956, the contract for the airframe had gone to North American Aviation, and the rocket engine was to be built by Reaction Motors. After the contract had been awarded to North American, and before the launch of Sputnik in October 1957, North American had considered making an X-15B orbital spaceplane that could carry a crew of 2 by launching it into low Earth orbit on top of a pair of SM-64 Navajo missile boosters. If this had been done, it could have predated the Space Shuttle by over 20 years. However, after Sputnik, the X-15B orbital spaceplane idea was shelved and revived several times until it was finally overtaken by the Mercury space program when NACA became NASA in 1958. In 1960, NASA considered using the B-52 and X-15 as a launch system for the Blue Scout rocket to carry small satellites into orbit. The B-52 would be the first stage, with the X-15 being the second stage carrying the Blue Scout, which will be the third stage to 180,000 feet before it was launched carrying the payload into orbit. This idea of using high-performance aircraft as launch platforms is now gaining interest once more as a method of launching the new generation of nano-satellites into orbit. 3 X-15s were built and performed 199 missions over a 9-year period from 1959 to 1968. Due to delays in the engine development, the first 24 flights used 2 smaller XLR-11 engines, but in 1960, the XLR-99 engines were fitted, over tripling the thrust to 57,000 pounds, and these would be used throughout the remainder of the flight programs. The X-15 generally performed 2 types of research flight paths: level high-speed runs at around 100,000 feet and altitude runs where it would try to fly as high as possible. Because of the speeds that the X-15 could reach, the temperature on the exposed areas like the leading edges of the wings and the nose could reach 1200 degrees Fahrenheit or 650 degrees Celsius at Mach 6. The fuselage was made from titanium and covered in Inconel X, a nickel-chromium based superalloy used to make the thrust chamber in the Saturn F1 engines, and could withstand the high temperatures without weakening. Although Inconel was capable of withstanding the heat stress, the stresses that built up between the hot and cooler areas was causing concern, as NASA was looking at testing a hypersonic ramjet engine that in theory could push the X-15 to around Mach 8. That's around 6,000 miles an hour or 9,900 kilometers an hour. NASA were also looking for an ablative coating. That's a layer of material that burns and turns to gas to protect the structure underneath, and could easily be applied to reusable spacecraft to cut the refurbishment costs and turnaround times. The X-15 would be an ideal testbed for this type of heat shield. After a minor crash in 1967, the second X-15 was rebuilt and renamed the X-15A2. It was extended by 28 inches, about 71 centimeters, for the extra hydrogen tanks for the proposed ramjet engine, and fitted with detachable auxiliary fuel tanks that increased the flight time by 60 seconds. It was also coated in an experimental ablative coating. It took 6 weeks to apply the spray-on coating, and when it was done, the X-15A2 was now white instead of black. It was also fitted with a dummy ramjet to test the design, but during the record-breaking flight of October 3, 1967, it also revealed major issues. Data from the flight showed that in places like the nose cone and the wing edges, whilst the coating had worked, it also prevented the Inconel structure underneath to cool as it was designed, and it nearly brought about the structural failure of the X-15A2 due to uneven heat stresses that had built up. Also, when the craft reached Mach 6, the gases released from the ablator turned the cockpit glass opaque so the pilot could no longer see out of it. Luckily, one of the two windows had been fitted with a metal eyelid, which was raised before the landing so he could use the other unaffected window. Due to unexpected airflow problems, the temperature was so high that the dummy ramjet was seriously heat damaged, and 3 of the 4 explosive bolts which held it to the mounting pylon ignited. It was then ripped from the aircraft as the final bolt failed, and this put an end to the ramjet-powered X-15. It was said that the X-15A2 came back looking like a burnt-out firework, and whilst it was sent to be refurbished, the idea of the ablative coating was dropped due to the problems of getting an adequate depth of the ablator over the structure. Due to the research nature of the X-15, there were accidents and incidents with some of the test flights. There was only one fatal crash on the 15th of November 1967, when Air Force test pilot Major Michael J. Adams lost control at 230,000 feet with the X-15 entering a Mach 5 spin. There were no recommended techniques to recover from a supersonic spin, as no one knew what the X-15 would do in such a situation. Although Adams tried to recover it at 65,000 feet whilst travelling at Mach 3.93 and tumbling through the air, the X-15 broke up, scattering the wreckage over a 50 square mile area. As the 1960s drew to a close, and after the fatal crash, support within NASA for the X-15 project waned. Many of the major research goals had been completed in the years before, and now spacecraft were the new priority. The last flight took place on the 24th of October 1968, piloted by Bill Dana, and within a year the remaining X-15s were retired, and one of the most influential aircraft research programs was shut down for good. The 2 remaining X-15s are now on display in the National Air and Space Museum, Washington, D.C., and in the National Museum of the United States Air Force at Wright-Patterson Air Force Base. And as always, thanks for watching, and please subscribe, rate and share.